Welcome back to AI Paper Podcasts. You're here because, like us, you want that crucial edge, staying sharp on the latest AI research. Especially when it comes to making these huge models work efficiently. Today, we're really tearing into a fascinating paper. Lookahead routing for large language models. It tackles a problem anyone deploying multiple LLMs faces.
Absolutely. It's that core challenge. You've got a mix of models, big, powerful ones, smaller, faster specialists. How do you smartly direct incoming queries?
Right. You need a router like an intelligent traffic cop, sending each query to the best model for the job, balancing that top-tier quality with speed and, cost.
It's a tricky balancing act.
Okay, so before we dive deep, let's do the super quick summary. This is the parts you'll want for your short-form edits, the absolute key takeaways in about a minute.
Okay, first big point. Standard routers just look at the user's query. That's the flaw. They miss crucial context about the response quality, which only shows up later, so they often mess up on complex stuff.
And the breakthrough here is what they call generative foresight. Lookahead routing basically trains a small, lightweight predictor model to guess the semantic essence of potential answers without actually running the big, slow models. It's like predicting the future.
Exactly. And it does this using a clever dual-task training setup. The predictor has to learn two things: estimate the routing score and reconstruct the key features of the likely response. That forces it to capture that essential response information.
And the results, well, they're pretty impressive. Lookahead consistently beats the existing state-of-the-art routers. We're talking an average performance bump of 7.7%.
Yeah.
Plus, it learns way faster, up to 6.3 times more sample efficient.
That efficiency gain is huge.
Yeah, that 6.3x number alone should make everyone sit up. Okay, so that's the nutshell version. Let's really unpack this now, starting with why the old way of routing just wasn't cutting it.
Right, so the authors really zeroed in on this fundamental issue, what you might call the inference time blindness. Traditionally, routing is treated like a classification problem based only on the input query. Let's call it $6.
Okay, makes sense initially.
But the label you're trying to predict which model is actually best, TT dollars, that depends heavily on the quality of the output, ET dollars that model produces, did it actually answer the question well? But here's the catch. At inference time, when you need the routing decision fast, the router never sees ET dollars. It can't. Generating one $1 is the slow, expensive part you're trying to avoid.
So it's making a crucial decision based on incomplete information. It only sees the start of the race, not the finish line.
Precisely. And they did this neat preliminary study. You mentioned figure 1, right? They basically show what happens if you could cheat.
Yeah, they trained one router just on queries and another one that got to see the actual responses during training, like giving the answers.
And the difference was stark. Across benchmarks like Arena Hard, Empty Bench, even tough math ones like GSM-8K, the performance, the normalized scores jumped up significantly when the router knew about the response content.
So the information needed for good routing is definitely in the response. It holds the key signals.
It absolutely does. But that's the practical hurdle, isn't it? If you need to run the full LLM to generate the response just to see if it's good before routing, well, you haven't built a router, you've just built an expensive ensemble. Defeats the whole purpose.
Right. Okay, so that sets up the problem beautifully. How does Lookahead actually get around this? What's the core idea?
The core idea is quite elegant, actually. Instead of generating the full response metaless, they train a small, efficient model, the predictor, $5, to generate a compact, latent representation of it. Let's call it $. Think of it as a semantic fingerprint or a compressed summary of the potential output.
Okay, so not the whole text, just a kind of signal, a vector that captures the essence.
Exactly. A dense vector that encodes key information about what that response would be like. And the key is how they train this predictor $5 and the router classifier $. Together. They use this dual task training objective.
Dual task, so doing two jobs at once.
Yep. First, there's the main routing job, the Latent objective. This trains the classifier $2 to predict the best model, using both the original query some dollars and these predicted latent footprints from all candidate models. Standard classification loss, like binary cross-entropy.
Okay, but if that was it, the predictor $5 might just output garbage, right? How do you ensure that tilde is actually meaningful, that it really captures the response quality?
That's the clever part. That's the second objective, the auxiliary loss, like Gardaspol. It's a reconstruction loss. This part of the training forces the predictor $5 to generate footprints tilde-C that are good enough to reconstruct the essential features of the actual ground truth response pyroller.
Whoa, okay. So it's like saying to the predictor, your footprint tilde-C has to be so information rich that someone else could basically figure out what the real answer why Ryler's was just by looking at your footprint.
That's a great way to put it. It puts pressure on tilde to capture what matters about the response, its content, its style, its likely quality. If tilde is a good summary, then the classifier seller looking at these summaries can make a much more informed routing decision, almost as if it had seen the full responses.
That makes a lot of sense. It's like getting the benefits of seeing the output without paying the full price.
Yeah.
Okay, so they have this core idea. How did they actually build it? What kinds of models did they use?
They explored two main architectural approaches, leveraging existing model types. One based on causal language models, CLMs, and one on masked language models, MLMs.
Okay, let's take the CLM one first, the sequence level predictor.
Right. For this, they used a small CLM, something like small LN2, which is only 135 million parameters, tiny compared to the models it's routing for. The input is the query $6, but they append a special token, a model identifier token, 99 details specific to the candidate model tool they're evaluating. And the predicted latent footprint, tilde is simply the hidden state vector from the CLM at the position of that $my token.
Ah, clever. So you don't need to wait for the whole sequence to generate. No autoregressive decoding needed for the prediction itself.
Exactly. That's crucial for speed. You run one forward pass of the small CLM over the query plus the special token, grab the hidden state at that token's position, and boom, that's your latent footprint tilde. Super efficient.
Okay, nice. And the other approach, the token level predictor using an MLM.
This one's structurally a bit different. They used a masked language model, like a modern Burke-base. Here, the input is the query $6, followed by placeholder slots for all the candidate models at once.
All models together. How does that work?
They append a sequence of repeated Métis tokens, essentially mask tokens, one set for each candidate model, taken, say, tall tokens long, as a placeholder for the response. The MLM processes this whole sequence.
Okay.
Then, the final routing decision is typically based on the output representation of the special CLS token, which, through the self-attention mechanism, has effectively attended over the query and the predicted latent representations for all candidate models jointly. Interesting. And this is where that special training trick comes in, right? The curriculum masking. It's not standard MLM training.
Right. This is really neat. Standard MLM often masks random tokens, but here they found it was much better to use a curriculum. They start by masking tokens only at the very end of the actual target response, several dollars during training.
Masking from the end. Why? That seems backward compared to how we usually think about prediction.
Well, think about the task. You're trying to predict which model will generate the best completion or the most accurate final answer. Often, the crucial difference between a good response and a bad one isn't in the first few words, which might just rephrase the query.
Okay. The key reasoning or the unique insight comes later.
Exactly. So by masking from the end first and then gradually increasing the masking ratio towards the beginning during the early phase of training, they force the model to prioritize learning to predict the distinguishing, often later parts of the response. It aligns the MLM's pre-training objective much better with the downstream task of predicting response quality based on a prefix.
Got it. It teaches the predictor to look ahead to where the real action happens in the response. Okay, that architectural detail seems important, especially given the results they got. Let's talk evaluation.
Yeah, the empirical results are quite strong. They used a pretty challenging setup. 5 different candidate LLMs ranging from 7 billion parameters up to 34 billion, covering models like YAIO 1.534b and Llama 3.10b. A real mix.
A heterogeneous fleet, like you'd see in practice.
Precisely. And they tested it across 7 diverse benchmarks, things like AlphaEval2 and Arena Hard for instruction following, GSM-8K and Math for reasoning, and Human Evil MBPP for code generation, really covering the bases.
And the headline numbers, how did Lookahead actually perform against the competition?
It consistently outperformed all the baselines they compared against things like KNN, K-means routing, Smoothie, MLC, Zooter, and RouterDC, which was a strong prior method.
And that 7.7% number.
That was the average improvement in normalized score for the MLM-based Lookahead variant over the best competitor, RouterDC, across all those tasks. That's a really significant margin in this space.
Wow, okay. And you mentioned the MLM variant often did better, especially on certain tasks.
Yes, particularly on the open-ended instruction following tasks like Arena Hard and AlphaEval. These tasks often lack a single right answer. Judging quality depends on nuance, preference, and comparing responses.
Right, much more subjective.
And the thinking is that the MLM variant, because it encodes the latent footprints for all candidate models jointly within the same input sequence, its attention mechanism, especially feeding into that final CLS token, can perform a kind of implicit comparison. It's not just asking, is Model A's potential response good, but is Model A's potential response better than Model B's or Model C's? It captures that relative quality.
So it's leveraging the shared context.
Yeah.
The CLM approach, looking at each model in isolation with its MoMA token, wouldn't get that direct comparison baked in.
Exactly. The CLM approach evaluates each potential future in isolation, while the MLM approach evaluates them in context with each other. That seems to give it an edge for those comparative, preference-based tasks.
That makes intuitive sense.
Yeah.
Okay, let's double-click on the analysis they did, the ablation studies, for instance. They tried removing parts of Lookahead to see what mattered most, right?
They did, and the results really underscore the importance of that response modeling component. The recipe directive we talked about, the part that forces the footprint ~t to be meaningful.
What happened when they took that out?
Performance just fell off a cliff. It wasn't a small dip. For the CLM variant, the absolute score dropped by 6.2 points, and for the MLM variant, it dropped by 6.8 points. Huge drops.
So that generative foresight, predicting the response essence, isn't just a nice-to-have feature. It's absolute core to why this works.
It's the engine driving the performance gains. Without that pressure to accurately capture response semantics, the router is basically back to guessing based mostly on the query, and performance suffers badly.
And this directly connects to that incredible sample efficiency number you mentioned earlier, the 6.3x gain.
Yes, exactly. Look at figure 5A or 6A in the paper. When they included the response modeling objective, the model reached the same performance level as the query-only baseline, using only about 16% of the training data.
15%. So you need drastically less labeled data, less training time, less compute to get to the same result.
Or, with the same amount of data, you reach a much higher performance ceiling. That 6.3x improvement in data efficiency is massive for practical deployment. Think about the cost and time saved in curating training data and actually running the training jobs. It makes sophisticated routing much more feasible.
That's a huge practical win. Another thing that stood out was the specialization awareness. You want a router to know which model is good at what. Did Lookahead show that?
It really did. Table 4 shows the routing proportions. For example, on the code generation benchmarks, human evol and MBPP, the Lookahead router learned to send 100% of the queries to the specialized coding model they had in the pool, the Quinn 2.5 Coder 7B Instruct.
Perfect specialization. It didn't waste compute sending coding tasks to a generalist model.
Nope. It learned the strengths. And interestingly, it also showed its biggest advantage on the hardest queries.
How so?
They looked at queries where only a single candidate model actually produced the correct answer, Table 5. These are the tough ones where most models fail. Lookahead had its highest win-loss margin against baselines on exactly these queries.
So when it really mattered, when only one model held the key, the response-aware features helped Lookahead pinpoint that outlier.
That seems to be the case. Those subtle signals in the latent footprint, hinting at a potentially correct but unusual response path, were enough for Lookahead to make the right, non-obvious choice.
Okay, one last crucial check. Efficiency. All this cleverness is great, but is it still fast? Does it add a lot of overhead?
That's the beauty of it. The overhead is remarkably low because they're using these small predictor models, small M2, modern MERP base, and efficient prediction mechanisms, single forward pass for CLM, joint encoding for MLM. The added compute cost is minimal compared to running even one of the large candidate LLMs.
So compare it to something like an ensemble where you run all the models.
Oh, way cheaper. An ensemble might activate, say, 83.8 billion parameters total in their setup example. The MLM Lookahead router adds an overhead equivalent to about 17.37 billion activated parameters, significantly less than running even the smallest candidate LLM fully, and a fraction of the ensemble cost.
So you get state-of-the-art routing accuracy, potentially better than anything else, and it's still very cheap and fast at inference time.
That's the key takeaway. It's efficient and effective.
All right, so wrapping this up, what's the big picture here? What does Lookahead routing ultimately bring to the table?
I think it successfully bridges that gap we've always struggled with in routing.
Yeah.
The trade-off between just looking at the query, fast but inaccurate, and looking at the full response, accurate but slow.
It finds a middle ground using that lightweight generative foresight.
Exactly. By predicting that compact semantic footprint ~t, it captures enough information about the likely response quality to make smart, specialization-aware decisions without the high cost of full generation. It's a really promising step towards building more intelligent, adaptable, and efficient multi-LLM systems.
Now, no paper's perfect. Did the authors identify any limitations or areas where Lookahead still struggles?
They did point out one interesting case, particularly in mathematical reasoning tasks like GSM-8K. Often, different models will start their response by simply restating the problem description from the query.
Ah, so the beginnings of the responses look very similar, even if the later reasoning diverges.
Precisely. The first dozen or so tokens might be almost identical across models. If the predictor $5 is mainly looking at the shared prefix to generate the footprint tilde t, it might not capture the crucial differences in reasoning quality that emerge later in the sequence.
So it could be misled by the similar openings.
Right. So future work might need to look beyond just using a fixed-length prefix or the initial hidden states. Maybe developing methods for adaptive span identification, figuring out dynamically which part of the potential response is most informative for routing, rather than assuming it's always the beginning.
That makes sense. Adapting where it looks ahead.
Yeah.
Okay, before we close out, let's leave our listeners with that final provocative thought. What's something to really chew on from this?
Well, think about this. You have a small, relatively simple router model, maybe just 135 million parameters, and it learns to predict, with pretty good accuracy, the quality of output from a vastly larger, more complex model, say 34 billion parameters, using only these compressed latent features.
It's like a huge compression of the big model's behavior.
Exactly. It suggests that a significant amount of the semantic intent or likely quality of a complex generation can potentially be captured in these surprisingly compact latent spaces. So the question is, how much complexity can we really squeeze into these footprints? And could we extend this look-ahead idea beyond just predicting quality? Could we train predictors to estimate things like, say, the factual correctness or the safety score or the potential toxicity of a response before we even generate the first token from the main LLM?
Wow. Proactive quality control using latent space prediction. That's definitely something to think about. Fascinating implications.